Well, welcome back to the morning session. Our first speaker is Peter Wallace, and his talk will be in Latin. He's going to speak about Homo vitro fragilor.
Okay, well, thank you. It will not primarily be in Latin. I'm going to turn on the mic. Is it on? No, it's on, I think. Now it's on? It says, okay. Yeah, it's with some trepidation that I chose the title for today's talk. It's actually the title of a homily by St. Augustine, which I hope you'll see has some relevance to my scientific topic here. My trepidation comes from two sources. Probably many of you know that today is Holy Saturday, the day when Jesus went into hell, according to some myths, and came back out of hell. And I'm an atheist, so I'm really worried about things like that. The other is, of course, Tony, who I've known for quite a long time, is a classicist. That also was part of the reason I chose the title. And it's very troubling sometimes to be around him in these sort of classical settings. I was in the Center for Advanced Study, and there was the director of the center was a guy named Lattice Gusta, who was a linguist, and Tony and he would go off onto Latin sort of rants every now and then I would try to imitate it back, and then they would all start laughing, other people as well, because they say, oh, you didn't, it's in pectore, not in peccata, and things like that. That's actually real, Tony. If you remember, and the whole group broke up. Probably the Center for Advanced Study at that time was probably the only place other than at the Vatican where Latin jokes were considered normal. Anyway, what does Augustine say? Well, first of all, why Augustine? Well, the title means that man is more fragile than glass. And Augustine's homily is a reflection on the briefness of life, probably not the right topic for an 80th birthday celebration. But in glasses, that's one of the major issues. Glasses, although in many respects appear to be very stable and very solid pieces of matter, they actually are transitory. And I think that's part of their attraction for understanding for theoretical physicists, because in many ways you can describe them by the laws of thermodynamics, but we know that there's got to be some way in which those laws are slightly inadequate or perhaps entirely inadequate. Because of this, why do I say glasses are transitory? Well, if you're a mineralogist, you would say there are no glasses. In geology, minerals are defined as crystalline substances. There are only a very few naturally occurring materials that are glasses. Amber, which is an organic material, is a glass. Obsidian is also a glass, but obsidian is very young. Typically, obsidian is less than 1 million years old. And the reason is because almost everything in the fullness of time becomes its lowest energy state, which generally for simple substances is the crystal. Of course, we don't, in our normal world, we don't have the fullness of time. And so we encounter glasses through technology. This technology actually is highly identified with the Romans. We normally think of everything being invented by the Chinese, but the Chinese actually admit that they got most of their glass from Rome. And so most of our glassy materials are made artificially. And so if we try to find the oldest glassy materials, we find these Roman pieces of glass. And this is a typical one. It's a beaker to drink from. And this quote concerns the lifetime of beakers of things made of glass. I'm sure that Tony has fully translated it, but I won't ask him to translate it. I'll let the computer provide the translation. And again, for the Easter week, it's probably not a bad thing to have a reflection on, are we not frailer than if we were of glass? For even if glass is fragile, yet if cared for, it lasts a long time. And you find grandsons and great-grandsons drinking out of the cups of their grandfathers and great-grandfathers. There's been some debate on this translation. I always thought Avis was uncle, but okay. This is really one of the problems with resolving the issues about glasses. Their behavior is really about something that does change. You can see that this beaker probably is not the way it originally looked. But they take a very long time to change. So many of the questions we'd like to answer about glasses, we could only answer really in cosmological time by direct experiment. Now, despite the fact that a glass is a non-equilibrium system, many of its properties depend on something that we call the temperature. When someone puts a thermometer in your mouth, I guess nowadays it's an electronic device, but when I was a child, it was made of glass with mercury inside of it. And despite the fact that the glass was a non-equilibrium system, we thought it was actually telling you your temperature. So there are characteristic temperatures at which things happen in forming glasses and in the behavior of glasses. And there's also some other variable that might also be described as a temperature that tells you something about how the glass came to be. So this is sort of a plot of some of those. The higher temperatures here are classical, and I'm going to mostly be talking about those. They don't involve h-bar other than h-bar setting the size of atoms. The lower temperatures on this scale all involve directly h-bar, like the Dubai temperature, the very low temperature below the Dubai temperature where these so-called two-level systems are found, which Tony posited many, many long years ago, and which he also returned to as the topic about the time around the early 90s. I will only say a little bit about those h-bar equals 1 properties, but I think the later two lecturers will talk about those a great deal. One of the reasons is that I hold that these h-bar equals 1 properties that show up at low observation temperature really are relics of the phenomena that trap the glass in its frozen, relatively frozen state at the so-called glass transition temperature, and that a lot of the universalities that we see in the low temperature properties reflect universalities about the glass transition itself. Now, one of the scales on this is, in fact, a temperature called Tg, the glass transition temperature. And as I'll explain in a moment, that's something that depends on how the glass is made. I can change that glass transition temperature up and down by making a glass rapidly or slowly. But almost all ways of cooling things are really still slow on a molecular scale for atoms and molecules. And so we don't have a large range over which we can vary these things typically. And of course, we're set, a glass is something that basically cools 1 temperature unit in 1 hour. That's a standard definition of Tg. So that's a fairly slow cooling of a glass. But you can see that, if you want to cool it much, much slower, you have to have much more obedient graduate students. And if you go, if you really want, and so there's a lot of experiments on more slowly cooled glasses, but they also run into problems, like people open the refrigerator while the experiment, or the oven typically, while it was heating, and you have to throw some of the data out and stuff like that. Well, what is the picture, the theoretical picture that goes along with this? Well, the glasses are not as well defined in structure as most crystalline substances. That's actually their beauty. They're very flexible, designable, and malleable. And this is why we can make them. They don't have one particular structure. They have many structures. And about 30 years ago, when I was here at the University of Illinois, I started to look at this problem and came to a way of looking at it that sort of was, I would say, a very modest extension of the theory of freezing. The idea was that basically you could apply the same theories of freezing into a crystal into freezing into aperiodic structures. And then the only thing that was different, but it's actually quite different, is that there's not just one aperiodic structure, but there's a thermodynamically large number of aperiodic structures. And this sort of picture, which I actually think I first talked about at Hans Frauenfelder's Fest in this room 30-some years ago, is the picture which is now called the random first-order transition scenario of structural glass transition. This is actually a slide from back in those days. I guess we called it a scenario now. Then, I call it a theory now. Other people still call it a scenario, but we'll come back to it. So what happens in this scenario? There's a relatively high temperature above which there's no sense of talking about any structure at all. The individual structures last only the time that it takes a molecule to collide with its neighbors, practically, or a few times that. But below a certain temperature, you become caged in the particular structure that you're found in at any one time. And this caging means that there's a free energy minimum in which you vibrate only, say, a tenth of a particle spacing before you run into another guide. This is very much like the Lindemann criterion in melting. There's a certain temperature at which there would be a Lindemann criterion for being caught in a cage. This temperature is called TA. At this temperature, fluids are really not all that viscous by our standards. Their viscosity is about 100 times that of water. And what happens is that as you cool below that, you now start to see a very strong dependence of the timescales on the temperature. And what's happening is that this metastable minimum, there isn't a single one. There's actually many states in which you can be trapped. There's a thermodynamically large number of them. And this thermodynamically large number is reflected in what's called the configurational entropy. This is a quantity that can be determined by calorimetry, basically by measuring the heat capacity and subtracting off the heat capacity of vibrations. There's, of course, some debates exactly how you do that. And what you find is that entropy is going down and down and down as you cool below. And there would seem that there would be a temperature at which that entropy would go to 0. Well, in that case, even though you have a disordered structure, there's only basically one of them. And so, obviously, you can't move there at all. That would be an ideal glass. So, in this picture, the glass transition is a relic of this transition that occurs when you run out of entropy. Now, how do you move at all in this temperature regime? Well, if we had a crystal and it was changing to some other crystal, or then when we have a single crystal changing to another crystal, we would develop a nucleation theory. We would take a certain structure, we would cut a little bit of it out, we would stick in the other crystal structure. Within the crystal structure, the energy would be somewhat different from where you started. And then, of course, at the border of the region that you cut out, there will be a mismatch. The energy will be higher. There will be some kind of surface energy. And what happens is if you're in a high energy crystal, it will eventually form the lower energy crystal by a nucleation process. And there's a free energy, which is a function of how big a region gets turned over. It might favor the lowest energy structure by a certain amount, but it's costly to do this because there's this surface term. If you're nucleating a crystal out of a liquid, then the liquid is actually a set of different structures, and it's favored by an amount which is the configurational entropy. So this is more or less the Zildovich-Frankel theory of nucleation, of forming a crystal out of a liquid. What's different if you have many such structures? If you have many such structures, you'll be able to find another one with nearly the same energy that you started with. It will actually have an energy that will vary around it. But now, when you're in that particular minimum, there still is an advantage to going to some other structure because there's exponentially many, and it's an exponential number that grows with the size of the system. So the driving force to move out of any minimum is this configurational entropy. And the only other technical difference is because there's many such structures, the scaling of the mismatch term would seem to be more like n to the 1/2 rather than n to the 2/3 in 3 dimensions. One way of looking at this is something I call the library construction, which is relevant to the quantum properties. Of course, we have many structures to start with. This is listing their energies. Just putting them for any finite system up in a list. Let's imagine taking a region and allowing a few particles to move around it we would then have only a few other states to which we connect. If I now have a larger region, there's more states. And eventually I get back, if I move enough guys, to the original library that I had before. And so this nucleation is really something being driven by this sort of entropy growth as I move out. What are the predictions of this theory? Well, there's lots of them. As I mentioned, this is something which we started 30 years ago. One of them was something that was empirically known, although it's amazingly disputed. This theory would predict, as was known experimentally, that the temperature at which you run out of entropy is also the temperature where you can't move anymore. Well, when you look at something like the viscosity of a liquid, which is proportional relaxation time, it doesn't behave typically in an Arrhenius fashion. A simple log versus 1 over t plot is not a straight line. It's highly curved. And the curvature had been fit by people with the so-called Vogel-Fulcher law, and it has a characteristic temperature T0. This T0 has been determined for hundreds of substances. The temperature at which you run out of entropy has also been determined for hundreds of substances. They are essentially the same. People sometimes dispute this, but we actually, my student Vasupchenko, who Tony was on his PhD thesis, we just had to actually make a plot. And that's a plot of the T0s determined by purely thermodynamic measurements, the temperature of vanishing entropy determined by purely thermodynamic measurements, and this T0 in this fitting form. And you can see they lie not just in a correlated way, that's the line with slope 1. People always argue about this because they say, oh, it involves an extrapolation. Well, the theory has another consequence, the one that I just described. If you say, what is the slope of the curve at the relaxation time that corresponds to an hour, that activation enthalpy is called the M value when it's written to the base 10. The glass people are technical people. They use base 10, not base E. And the theory actually predicts that that depends on the temperature. It depends primarily on the heat capacity change when you get trapped. That's measured. So the theory actually predicts the Arrhenius slope at the point where the relaxation time is, let's say, an hour. That's called the M value. This theory, the random first-order transition theory, predicts that it's a very simple formula, something like 35 times delta Cp. It's a delta Cp per particle, so things are not always made of simple spherical particles, so you have to normalize this by the entropy change on melting. In order to see what it is per particle. This is the comparison of the theory and the experiment. It's not, there's no adjustable parameter in that graph. That's the line of slope 1. Now, maybe that comes from good living, but I would say that's a very strong prediction. The reason why there's this dependence entirely on the entropy is that the free energy cost of making an interface is primarily also entropic. And it depends on this cost to localize a particle to a Lindemann length. A Lindemann length is about 1/10 of a particle spacing. It depends logarithmically on it. And so even if you're off by factors of 2 in the Lindemann length, you're only off by a little bit in the surface energy. And again, this comparison involves no extrapolation at all. One of the other characteristics of this, then, is because the surface energy at Tg is a more or less universal thing through this entropy loss of localizing to a Lindemann length, the size of a region which is flipping over and changing structure is actually fairly universal. It's 4.5 in the theory times the size of an individual bead or particle. How could we figure out something about that size? Well, indirectly we do, because every region doesn't have exactly the same energy. Instead, the energy fluctuates. And so there's actually a range of activation barriers when you look very carefully at the relaxation phenomenon glasses. And the range of barriers can be predicted knowing this size. This has been turned into a very nice analysis that's actually slightly more rigorous by Giulio Baroli, Jean-Philippe Bichot, and Berthier in the early 2000s. And so you can back out from measurements of how non-exponential relaxations are a value of the correlation length. And this is done for about 50 substances by them. And you can see that the value is somewhere in the vicinity of 4.5 or something like that. My colleague, Martin Grubeli, asked what could he do that was interesting with a scanning tunneling microscope a few years ago. And I said, well, why don't you look for these regions? So he actually looked for these regions at the surface of a metallic glass. And again, he would have a movie here. If I had more time, I'd show you the movie of what these regions look like. And they're about this size of 4.5. How is this related to h bar equals 1? I know Philip Phillips says he hates h bar equals 0, so I did have to put something in about this. As I said, you're growing these large numbers of states until finally you get over to the same state you had before when you've rearranged the entire system. The size where you basically get to a state that's nearly resonant with where you were before is also roughly this correlation length. And you can now say that if you want to look at the distribution of states in the vicinity that you might be able to transfer through resonant tunneling, then you would say, well, it's basically something which is given by the entropy variation with energy at the glass transition temperature. The energy scale is set by the glass transition temperature. And then you also have this size. So this predicts a number, a rough number for the, that's universal for most, for these substances, or always in the range of about a density of states of 10 to the 45 per joule per cubic meter. I think this is Voss wrote this down. I'm a CGS person myself. You could also take the data that are measured here, and you could say what would be the correlation length that would make that exact. And you can see here the correlation lengths are probably a little bit larger, between 4.5 and maybe 10. But in the view of Voss and myself, it's these resonances which you're accessing, or these resonances are accessible in the low temperature properties of glasses. There may well be other kinds of excitations, but these are intrinsic to having formed a glass. And this number is one of the numbers that's involved in the universality scenario that was sort of uncovered by, experimentally to some extent by Andy Anderson here, and then that Tony has said a lot about. But that's about all the quantum mechanics I'll talk about here. One of the things is that in doing, you see there's kind of a no man's land between what goes on at these temperatures near the glass transition and the beginning of the ability to be trapped in the minimum. One of the reasons why it's hard to be trapped at the minimum at the high temperature is that if you make an object which is not a sphere, a rough sphere as the region to reconfigure, but if you make it be more varied and fractal in its shape, you get an additional entropic contribution, a contribution that comes from counting the number of ways you can move. Well, one idea would be that those things that are the things that you would expect those to be are things that are called lattice animals, and they're roughly percolation clusters. They have an entropy that grows linearly with n. And so you have an energy cost of mismatching things that's linear in n, and you have the entropy gain that you get because there's many different states, and you get an entropy gain by trying to figure out what the shape is that you would want to make. So above a certain point, this is a completely downhill process, and that's why you can't be trapped. So this allows you to predict the temperature at which you start to get the non-Arrhenius temperature dependence, this crossover temperature. And the theory of this is actually very similar to the theory of what's called the Hagedorn transition in string theory. And at least before the last few years where this ADS stuff came in, I said, well, this shows that string theory is a theory of something, but perhaps not a theory of everything. So actually, as you can see, this is a comparison of the experimental TC minus TG versus this 1 over delta CP. It's predicted to be straight, to be a slightly curved line. Well, what about glass being fragile? You know, we have this impression, and certainly St. Augustine had this impression, it's very fragile, but actually, how fragile is it, and why would it be less fragile than us? This is a thing from the Corning Museum of Glass. What they're doing is an experiment that was done by a guy named Prince Rupert, I think in the 18th century. This experiment was good enough to get him in the Royal Society. Making glass by pouring it into water, it's cooling. It's cooling somewhat inhomogeneously, so on the outside it's more stressed than it is on the inside. And actually you can see that this piece of glass is extremely strong. He's doing this with a pair of pliers. He's now hitting it with a hammer. We know if we hit people with a hammer, they get mad at you. But now look at this. He's going to now break the surface of the glass, and we'll see that it blows up. So what's happened is this cooling process has put into the glass some stress. That stress is enough energy to blow the whole thing apart. Apparently, Prince Rupert went around in London showing people this and then blowing this up in their pockets or their hands or whatever, and the king thought it was very funny anyway. So why am I showing this picture? Well, a lot of our interest in glasses is indeed their mechanical properties. And so one of the things that we did a few years back was to see how does stress affect the process of being trapped in a minimum. And you can see from the Prince Rupert drop experiment that if there are stresses, there's stored energy. Well, if there's stored energy, then when you try to reconfigure a region, you gain back not only the configurational entropy of all the other states. If the material was frozen in and was actually frozen glass, you now could access states that are lower in energy than you started out with. That's part of the so-called aging process. And then on the other hand, you also can go to a non-stressed configuration. So you lose an amount of stress, an amount of energy proportional to the square of the stress. The coefficient in that is something that involves a calculation that would be familiar to anyone in damped. It's basically the calculation of the intrinsic viscosity, but for something with more elastic constants. It's elasticity rather than hydrodynamics. So this actually predicts the actual strength of glass. So this is the formula from Opiwat's, in my paper. Opiwat was one of my students at Rice. First of all, the strength in general comes out to be proportional to the elastic modulus itself. It also involves a temperature, and then it involves some corrections that depend on how much stored energy you have and the entropies. Well, first of all, the amazing thing about glass that's been known for a long time is glass actually is very strong. In the 20s, I think, or maybe the 10s, Frenkel calculated the limit of strength of a material by rolling one lattice over another, and he got a very large number. It's also proportional to the elastic modulus, and the strength is shown in that purple curve as the Frenkel limit. Crystals are much less strong than that, like 100 times less strong, which of course led to the theory of dislocations, which I think is one of the great contributions of solid-state physics in the 20th century, I think sadly not recognized by the Swedish people. But what's weird is, of course, a glass doesn't have any obvious places to put in dislocations. And that's why it is much, much stronger. And by this analysis, it goes about 1/3 to 1/2 of the way to the Frenkel limit. If we could make glasses on much longer time scales, we could lower the glass transition temperature and we could make much stronger glasses. This is not very possible for the reasons I just said in a direct way of making glasses, but it is possible to get lower energy glasses by a vapor deposition process. And one can get basically glasses that are about twice as strong, we think, as the glasses we have today. The problem is, of course, making anything by vapor deposition is very expensive and probably only good for coating your glasses, so they won't scratch. One of the other things that you saw in the Rupert's drop experiment is things are cooling and they're storing stress then by the volume contraction. And recently, Vas Lubchenco, with whom I still collaborate, because he's a professor at the University of Houston, we were thinking about this, and we realized that this would allow us to understand what would happen if I was able to really quickly compress things in a way that was sort of different from the cooling. When something, before it's compressed, it actually has this stored stress. The stored stress depends on the fact that it could become an equilibrium fluid inside the region, which is being reconfigured. That would then lower the pressure. By lowering the pressure, you get some pressure volume work. And you can compute that. And now what you find is a very interesting kind of diagram. Some people would call this a phase diagram. In mean field theory, it actually is a phase diagram. But in this theory, which goes beyond mean field theory, it turns out we just have to call it a diagram. And the reason is that most of these states are not equilibrium states. They're states that have, say, pressures quite different from the equilibrium pressure, which can happen if I'm able to cool something really, really fast. What one finds then is that in addition to this instability point that was predicted on the equilibrium curve, that curve becomes extended as I allow the system to have very different pressures than the equilibrium pressure. And it allows us to have a spinodal that extends all the way down to infinite external pressure. Well, that corresponds to what's called a jammed system. And so the jamming system, again, in equilibrium theory, has been shown to be related to this spinodal point that we have here. This is kind of an extension of the theory. It says that really the jamming phenomenon is itself a glass transition and depends on how rapidly you can really jam things. And this will be very interesting as a way of thinking about the jamming problem, about which there's other approaches. One of the ways this might help us back in the quantum problem is it might be possible to make jammed materials and study their quantum properties. Some people actually hold that all the two-level system properties come from being near this jamming transition. I think that that's kind of a question in this language of what is the shape of the region that reconfigures. But we'll see how that develops. This is actually a paper that should come out very soon in Ben Whittam's Festschrift. Well, you can see that you could make a glass which is very fragile because it could be marginally stable. Well, I'm in a center for theoretical biological physics, and this is one of the reasons I'm still allowed to study this and get paid. The inside of the cell is very likely a marginally stable glass. It has very large objects. Because of their being large in size, they don't move intrinsically very fast, which is why what for a molecular liquid is 1 hour corresponds to a microsecond in this world, or an hour for colloids is really a microsecond relaxation time for cellular things. And so cells really have assemblies of particles in there that are very near to this marginally stable point. And of course, in this sense, this would explain why cytoplasms are indeed more fragile than the materials that than inorganic glass. So with that, I went over, I'm sorry, but I'll go to the last slide for Tony. I understand that this is actually addressing the birthday itself, the best of birthdays. It's vocative. Oh, best of birthdays, and many more years. Thank you, Tony. Thank you.
All right, questions? Yep.
Yeah.
It's indeed strong. The trouble is it's not tough.
Mm.
That's why it's fragile.
Yes.
Like rubber, it's not tough. And I wondered whether how you would apply the ideas you were presenting to this very low crack propagation energy result, which is of course related to its inability to support dislocations.
Well, okay, there's a lot there, and we haven't worked all these things out. What sort of happens and why it shatters sort of catastrophically is it's so strong that once you put all this stress energy in it, it has enough energy to actually fracture things by breaking bonds. In the phase diagram I've shown here, there's no gaseous state, if you will. There's no state that just involves the particles no longer adhering. So to some extent, that's one of the features. I think the chemical, the materials people, in the attempt to make tough materials, is that to be tough, you have to take the energy and dissipate it. And so it is to make composites that are not glassy or just weakly glassy. Rubbers, in a sense, are glassy, but because the things that are holding the rubbers together are the crosslinks. The crosslinks are much larger, and so the density. So if we were to translate this theory into rubber, then everything goes down by the density of crosslinks compared to the density of atoms, and that's why rubber is, relatively solid, but it's got much more dissipation going on in it. So I think there's a lot of interesting questions there. One now starts to make, especially through deposition, materials that can be, a layer of glass, a layer of another material, a layer of another material. It's very expensive, but you can actually get things on length scales that are comparable to C. So there's also a large number of interesting experiments that one can do there about this length scale, and they may be practical for making stuff. Thank you. Okay. So, oh, there's more questions. Yeah.
Your last picture, Peter, have you ever thought about cell division in the language of glassy dynamics?
Not division per se, no. I mean, there's a lot of interesting questions in cell division back even at the chromosome level, which we're starting to think about. One of the problems is, and Apiwat's other project was actually turning this into a theory of the phenomenon known as shear bands. And so you actually can show that, but this actually gets you into, you can write down a generalization of the Navier-Stokes equation that also talk about how does this effective temperature change as I perturb a system and add stress to it. If you put those two things together, you get the phenomenon of shear bands. And that was meant to sort of also be just used to talk about the flows of the entire cytoskeleton, but we haven't gotten to that point yet.
All right, well, let's thank him again for a fantastic talk. And our next talk will be by Christian Ince on the breakdown of your cell here at Lattice at ultra-low temperatures. Interplay of frequencies.
Oh, yeah. Okay. Can you get it? I can't see it.
Great. Thank you. And here's the microphone.
I don't know. Thank you. It's a great pleasure to be here, and I feel very honored to have the opportunity to give a presentation here at this very nice and wonderful occasion. I'm going to talk about the universality of glasses, of the low temperature properties of glasses, a topic which caught Tony's attention very early on, and he had contributed to that with many fundamental papers. Now, I met Tony in person the first time, I believe, in Catania. This is a picture of that here. So we were both at a Italian spring meeting, and there were very few foreigners. There were other people than us. I mean, there were Steve Chu, and there was Doug Osheroff at the time. And whenever we walked into a lecture, they were normally given in Italian, they switched automatically in English. I mean, like miraculously. You may remember that. I was very impressed by that. And we had a wonderful time together. One day, there came a volcano specialist down from Naples and took Doug, Tony, and Steve up to Mount Etna. Doug took a lot of photo gear and made a ton of pictures, as he told me later on. What you might not know is what happened 3 days later, or you may know, I don't know. What happened 3 days later on the weekend was this. And I was glad this was a near miss. A day later, I had the opportunity to go up there, and it looked like this. So there was a wide lava stream, like 4 to 5 meters wide, 200 meters long, and it was quite impressive scene at the time. Now, and a similar impressive eruption occurred in the world of glasses in 1988, when Claire and Tony published this paper on the universality of glasses. It was more than on the universality of glasses. There were 3 points they were discussing. One was, that while the observed effects are mostly consistent with the two-level system model, they do not uniquely establish it. I think that's still a fact. B, that the model cannot explain the dramatic quantitative universality of the low-temperature behavior of amorphous materials. And C, that the neglect the lowest order within the model of the long-range interaction induced by the strain field, while self-consistent, is not imposed by the data. Very important questions, and I believe of the contents of the paper, Claire will talk about a little bit later on, but it generated a lot of interest, and other people tried to do experimental work along those lines. There was a bit later another follow-up paper in which Tony was asking the question, why are they so similar? I mean, what is the reason for the universality? And he stated in this paper that the universality is a totally unbelievable degree of chance coincidence. And I think that's really what it is. Now, what is behind that? I will start introducing the low temperature properties first, and will tell you then what is meant with the universality. Now, if you cool down a glass and measure the specific heat at the lowest temperatures, it deviates strongly from its crystalline counterpart. The crystal obeys the Debye law, but in the glass you find a large additional amount of excitations, and moreover, the specific heat varies linear with temperature, which indicates that you have a constant density of states. So there are additional excitations beyond phonons, and they are broadly distributed. Secondly, if you measure the thermal conductivity, you see that the thermal conductivity is much reduced compared to the crystal and has a different functional dependence. Peter was already pointing out this part here, where the phonons strongly interact with those low energy excitations. And the thermal conductivity as a function of temperature varies by T squared. Now, the universality is a fact which was seen here in Urbana by Andy Anderson and others. And it's the idea, or this is the observation, that no matter what glass you cool down, whether it's a polymer, a strongly bounded structural glass, or metallic glass, you find that in the regime, at lowest temperatures at least, you find that the properties almost identical. Not only that it's a T squared, but also the prefactor, the coupling to the phonons is still the same, roughly the same, within an order of magnitude. And that's very striking. So you can change whatever you can choose whatever composition, you will always find this. So there must be a reason behind that. Now, the canonical description still today for glasses is something which was published in 1972 in two independent publications by Phillips and Anderson and co-workers. And the idea is the following. In the matrix of glasses, you find atoms which reside in two minima, or you have reside in minima which are separated from a second minimum only by a small barrier, a potential barrier. So if you cut through that in the potential landscape, you will find this double-well potential, and you find those two positions here. And since the barrier is not too high, the tunneling probability becomes large, and at low temperatures, you can observe those tunneling processes. It leads to a tunnel splitting, which is given by the ground state energy times the tunneling probability. And in this parameter lambda, the microscopic properties, d, m, the mass, and the potential height are included. Now, since you are in a glass, you have a disordered environment, you have also a difference in the depth, possibly, of the two wells, which is accounted by this asymmetry energy delta here. Now, the bold assumption here, triggered by the specific heat measurements, was that the parameters are widely distributed, and in this case, it was assumed that lambda and delta are uniformly distributed over an arbitrarily wide range. That, of course, is an unphysical distribution function, so you have to cut it off at some point if you want to describe some data. But this describes very well elastic, dielectric, and thermal properties in glasses over a wide range of temperatures. Now, a few years later, after Catania, we met again in Dresden, and we had long discussions about the validity of this model, whether this is really a unique description. That was something Tony was moved by, whether this ad hoc phenomenological model could have another, or there would be another explanation for all these properties. And he convinced me and others that there is a need to look for a smoking gun experiment or to do research to identify better what the microscopic origin of those excitations are. Here's another picture of that conference with Spivak together. So we discussed a lot, I remember, and I really was convinced after that there needs something to be done. Now, Tony recently, a few years ago, sharpened this again, this question. So is there an unambiguous test for the TLSs in glasses? So in this paper, he also outlines an alternative. But more importantly, I mean, he really sharpened this question once again. Now, I will tell you now, there's one intermediate slide I forgot. So there's two things. The universality of glasses cannot be explained by the standard tunneling model that I already showed you, but it, of course, not excludes the standard tunneling model. It would be a huge coincidence in some sense. But the universality generates the problem that we cannot really look for the microscopic nature of two-level systems, because no matter what we do to our glass, the experimental results are the same. So I found this term from Tony, the Cinderella problem of glasses. I think you used that in one of your Waterloo lectures. I found it very nice. Now, let me tell you a little bit what happened in the last few years it started already a long time ago with something we didn't understand at all. This is here the dielectric susceptibility as a function of magnetic field. Normally, you wouldn't expect any magnetic field dependence in a glass which has no spins. So if you have a homogeneous dielectric, in first order, there would not be any magnetic field dependence because the electric field vector is a vector, and so we have a polar vector and an axial vector of the magnetic field, and therefore we wouldn't couple in first order. Now, what we see here are measurements of 3 different glasses as a function of magnetic field, and clearly one sees not only a magnetic field dependence, it was non-monotonic, which was very surprising. On the other hand, later on, echoes were done, microwave echoes. So you have 2 pulses, like an NMR echo, and you get a microwave pulse out of the sample. And the question there was, if I do this experiment in a magnetic field, what would happen? And you can see here 3 different glasses. For this optical glass here, BK7, you see again a non-monotonic behavior of the echo amplitude. It was very strange because at the highest fields, the coherence, this is what you measure with this kind of echo, was largest. There's no reason why the coherence should increase if you apply a magnetic field. Now, there was another glass, and you see already there are slight differences how they behave. But then when we looked at SiO2, there was nothing. There was an echo, but there was no magnetic field dependence. That's what we expected in the first place. Now, what was the reason for that? This experiment can be explained by a model I will show you in a minute, which doesn't explain this necessarily. Yeah? So the model is the following. If your tunneling entity carries a quadrupole moment, and you have in those in this double wells, different electric field gradients, then the nuclear spin, the nuclear quadrupole moment rather, is not happy on either side. So it does go into a linear combination of states. And since it can distinguish between left and right, it couples to the 2-level system levels to those wave functions here, and you get an intercombination spectrum. Or you can say simply you have a hyperfine splitting. Your 2-level system becomes a multi-level system. And the splitting here is the splitting what the nuclear quadrupole produces in this electric field gradient. Now, and then if you apply a magnetic field, of course, you Zeeman split those levels, and you can couple to the 2-level system directly. Now, it's already clear for SiO2 this is not happening because there is no atom in it which has a nuclei with spin larger than 1 or 1. Yeah? So there's only dipoles in there. Therefore, this was already a strong hint. Now, we tested that a little more rigorous in the following way. We use glycerol. Normal glycerol has only atoms with nuclei with spin 1/2 and no quadrupole moment, and you can deuterate that. You have the same kind of glass. If you cool glycerol down, it forms a glass. And then we repeated this measurement of the microwave echoes. So for the deuterated stuff, we saw a strong magnetic field dependence, and for the normal glycerol, there was basically nothing. A little bit of that, which we signed for dirt, which it wasn't, but this is not the topic I want to discuss here at the moment. Now, one can go one step further now. You can look again at zero magnetic field in the echoes. In the case of glycerol, you have 4 levels, which the one here is split by the quadrupole energy. So if you have 4 levels, and remember such an echo experiment is basically an interference experiment between those levels here. So if more than 2 levels, you get an additional phase factor, And this modulates the amplitude. So what you expect is that you get a modulation of the decay, yeah, a quantum beating. And we were looking for that. And this is here now in partially deuterated glycerol. You see here only the 5 hydrogen replaced by deuterons, which bonded to the carbon. And you see here very nicely in zero magnetic field these huge oscillations. And when you look at it, actually they have the right frequency, something you can determine at room temperature also with NMR experiments. When you go to large magnetic fields, what happens is subsides. And that's clear too, because if you have a large magnetic field across your double well potential, then in both potential wells, the quantization axis is given for the nuclear spin is given by the magnetic field. So they cannot distinguish left and right anymore, and there's no coupling to the two levels anymore. So in some sense, in whatever nuclear state the system is, it will look like a two-level system. That's exactly what you see here. So then we deuterated only those here, and this is a different quadrupole frequency, but also it showed that it sees more the environment, a decade faster, this oscillation, because this is differently bonded to the environment. Now you can go even one step further. You can model then, you can ab initio calculate what the echo amplitude is in magnetic fields if you assume that you have a rigid glycerol molecule just rotating a little bit in this matrix. This was an assumption we made and asked whether one could, in fact, microscopically describe that. And what you can see here, this is the blue line, and the points underneath are the experimental data, and the description is really, really nice. There's something you had to add, which we found when we did this. There's a nuclear dipole effect. I will neglect that at the moment, but this is also happening. And when you put all this together, this is here, if you subtract the exponential decay, you see the oscillations for the quadrupole model, and then for the dipoles, this is this long oscillation here. So we concluded at that point, I mean, this is the first time TLSs have been really identified in a glass. This is not a typical glass, this is a molecular glass, but it is a glass, and it has also those low temperature properties which fall into this universality. Now, the question was then, can we explain with the nuclear spins also the fact that the dielectric susceptibility is affected? And that's not obvious. The fact that there are 4 levels is not, there is no, I mean, this is not straightforward to explain. Now, what we did was first looked, of course, what kind of processes are happening. First of all, you have a resonant process if you couple an electric field or an elastic field to a two-level system. So it can make a resonant absorption or stimulated emission. Or you have relaxational processes because your electric field via the dipole moment changes the asymmetry energy. So this goes up and down over time. And therefore, the energy of the splitting changes over time. And the system wants to come into instantaneous equilibrium again by absorbing phonons and emitting phonons. And this takes place at lowest temperatures via the one phonon process. Yeah? That's all known. Now, if you integrate over all the parameters over this wide distribution, the tunneling model says we get a resonant contribution, which is logarithmic. This is a characteristic of classes. This is in some ways identical to the linear dependence in the specific heat. It's just reflecting that you have a broad distribution. And then at some point, system is fast enough at a finite frequency to contribute to the relaxational channel, and this is the red one here. So if you add this up, you find this minimum. And this is my point I want to make. We have a minimum here, and this tells you when the onset of the relaxation is. Now, you can then do this at different frequencies. These are all calculations. This minimum shifts with frequency to higher temperatures. And the way it shifts depends on the dynamics the system is doing. So the minimum shifts with omega to the power of 1/3 if you have the one phonon process. If you're a higher order phonon process, it shifts with the power to 1/7. So you can see here this already becomes sharper because the two phonon process sets in at those high temperatures. Now, we did then investigate a number of classes. These were classes, the first three here. They have almost no, they have no quadrupole moment or only very small ones in there. And then we looked for systems which had a certain amount of like holmium in this, which has a large quadrupole moment. In this particular case, you have 1% of holmium in the glass. The rest is almost the same. You can consider it as BK7 or something like that, but 1% of holmium is then there. Now, the question was, what would we see? So we measured first these standard glasses, Herasil. This is just a Si2 glass. You see perfectly what the tunneling model predicts. It shifts the minimum to higher temperatures when you increase the frequency. And that's also true for the system BK7, this optical glass. That's long known. Then we quantitatively analyzed that. We did this measurement over a very wide range of frequency up to the gigahertz range. And you can see all of those points, the minima as a function of frequency, fall on this line. It's the one phonon process. It also tells you that the one phonon process really holds up to 2 Kelvin or something like that, which wasn't so clear for a long time. But then we turned to those systems with a large quadrupole moments. And what you see here is at higher frequencies, there is still a smaller shift. This is with tantalum. So from 16 to 12, there is a small temperature shift. But then it stops doing that. And even more bizarre, if you go to the holmium glass, it seems to be completely identical, inert about the phonon relaxation. It doesn't shift anymore. And if you now measure to lower temperatures, something very bizarre happens. It becomes frequency dependent again at the lowest temperature, which it shouldn't, because the resonant process shouldn't be frequency dependent. So something very odd is going on here. And if we go back to our plot here, this is here our minimum temperature again as a function of frequency, and we put in our tantalum glass, it stops here, the minimum. But at higher frequencies, I didn't show those data, we measured really up to the gigahertz rate, it perfectly follows the one phonon relaxation. And for the holmium, it's even more striking. So it's completely in this temperature range here, in this frequency range here, the minimum isn't shifting. So this picture alone tells you one phonon relaxation is not the only answer here. You have the one phonon relaxation, and by the way, two phonon relaxation sort of is indicated up there. But something else is happening here. And the something else is a speculation I will give you of the following. We have the nuclear spins in those systems, the nuclear quadrupoles. Now, if you look at the specific heat they would produce, or how many degrees of freedom we have, in glasses, typically, you have the concentration of two-level systems is 10 to the minus 6. So 1/1,000,000th of an atom is involved in such a tunneling process. The number of phonons becomes very small at such low temperatures, but the nuclear, if you have 1% of holmium in such a glass, this is a huge heat capacity. And it's a huge bath. Now, if you assume that there is some kind of coupling between those two, then energy could flow into the nuclear bath from the tunneling systems. Your electric field is shaking your tunneling system, and it relaxes into the nuclear bath. That's something which hasn't been considered so far. The nuclear bath may drain over time to the phonons, but the nuclei phonon coupling is extremely weak at lowest temperatures. Yeah? It's days or weeks or something like that. And of course, we have some coupling to the phonons. So how does this happen? How does this happen? The idea behind that is the following. I have the our atom, which is tunneling, surrounded by a lot of systems which have spins. So when it tunnels, it has a huge, it has a huge deformation potential, so an elastic dipole or quadrupole, which is of the order of 1 eV, which is 10,000 Kelvin. So if you have 10,000 Kelvin acting here, all those surrounding atoms wouldn't stay in place. You perturb them. And I will put this, I would rather look at such a picture now. So if a tunneling system, it's not clear what you call the tunneling system here, but if you remain to say this atom here is the tunneling system, then the matrix around it moves a lot. And if it moves, it changes the field gradient. The field gradients of those atoms are changing. And since the field gradient talks to the quadrupole moment, so the tunneling system can talk to all the quadrupole moments in the surrounding, and energy can be transferred. So that's the local bars. About, if you do numbers, about 1 million nuclei in the surrounding are seen by a typical two-level system. And if you drive the system hard, we did that, you can also saturate that bars. But I do believe this is the right explanation. And since the number of two-level systems, the number of spins is not changing, and also not the coupling mechanism, there's no temperature involved. This mechanism has a constant relaxation rate. And therefore, we have this constant position of the minimum. So let me come to the summary. Nuclear spins are important in gases at low temperatures. The universality of gases breaks down at very low temperatures. I'm strongly believing that. The universality is an established fact over a certain range of temperatures, but it breaks down when the nuclear spins become important. It allows for material-dependent studies. That is good, because then we might answer some of the questions Tony raised for different kinds of gases. And also, for some systems, we were able to underpin microscopically that this is actually happening, that something is tunneling. At least, I hope we did that. And I think most importantly here, there is still no microscopic explanation why one has this universality. Yeah? We need experimental proof for some of the theories, and that's important. We should work on that. So fundamental questions need still to be answered. One has to think about it and work on it. And I think this is the forward-looking part. And I love this picture. It really shows who Tony is, a wonderful person. Thank you very much, and happy birthday. And I have a little something from good old Europe.
Slightly different from pure two-level systems. There are a few little interactions between them, but not terribly strong. I'm wondering if but nobody's tried to look for these magnetic field effects in such detail.
Yeah.
Is something that you think might be feasible?
Yeah, I mean, we have started on metallic glasses doing this. We have some preliminary results, and you can see magnetic field effects as well. The problem here is you have many, we look at these bulk metallic glasses which have different components. Most of them go superconducting at the lowest temperatures. And the ones which don't have still a lot of systems which have electronic spins in there. And this overshadows a little bit what happens with the nuclei. You have a huge Schottky heat capacity and such. But we're working on that. We're trying to go after that. Yeah.
Tony had a question. Tony had a question.
Do you have any thoughts about the plateau in the thermal conductivity, which seems to occur in most
Yes.
glasses?
No, I don't. Actually, I never really tackled that problem. I think that's beyond what two-level systems do. That's some other dynamics. I mean, many people think this is like quasi-harmonic potentials where you scatter. This would be part of that wide distribution. Somewhere the minimum is, the maximum is so small so that you can describe them almost as quasi-harmonic defects. But no, I don't. I'm sorry. Oh, sorry, I didn't repeat the question. If I have any thoughts on the plateau of the dielectric, on the thermal conductivity measurements. I didn't point out the plateau. This is just above the t-square dependence. Almost every glass exhibits a temperature-independent plateau there, and it's also universal in terms of the height somehow. I didn't get that.
What is the upper limit of the ultra-low temperature at which you are selecting the external?
Well, this depends on the material, obviously. I mean, for this glass with holmium, we saw this impact already at 390 millikelvin. That's where the minimum is. But this is a very special case. My personal viewpoint is, no matter what you take, it will eventually enter that regime and will show that the nuclear spins will contribute. The nuclear spins normally don't couple to anything, or very weakly to phonons at the lowest temperatures, but through the mechanism I was describing, they come into play again. And I think they will dominate everything as when you go really low in temperatures. It's an interesting thought, for example, if you look at the decay curve in an echo, you normally think this is dynamics, so with interaction with phonons. But I believe if you cool a glass to very, very low temperatures, then the decay is the interference with all the nuclear levels surrounding. So you will not see a constant echo amplitude, even if you switch off the phonons. You will see a coherent state. It's still coherent, but it goes down because of all the interference. That's my picture. We try to prove that, but it's hard. You have to go to very, very low temperatures. And with dielectric glasses, there are limits to that.
Thank you again for a great talk.
Yeah. Yes, you can.
This is going to.
Our next talk will be
This is for a different
on
mag.
low temperature
That's for different
properties
mag.
of glasses
Yes, here one.
beyond 2-level systems.
Okay.
Yeah.
This is just USB.
Yeah. The microphone.
I don't think this is working. Maybe I won't do that because it makes me do that. It's not identifying the keyboard.
I leave it here if you wish.
Okay, thanks. I don't think I want to install this. Okay. All right. Okay, so it's a great pleasure to be here. I think my earliest personal memory of Tony was in 1983 when I was a graduate student finishing up my thesis with Phil Anderson at Princeton. I sent an application for a postdoc to Tony, and he responded by trying to reach me at my father's house in Florida where I was for Christmas vacation. I wasn't home at the time, so my dad took a message. He called me and said, you know, there's a man, wants you to call him back. Name is Tony, Leggett, gave me the phone number. And my dad ended the conversation by saying, he talks funny. So anyway, I wound up coming here for a postdoc, and I think the reason that one of the reasons perhaps Tony hired me was because he was working at the time on macroscopic quantum tunneling, involving tunneling in the bath of phonons or bosons. And my thesis had involved tunneling in the presence of fermions, electrons, in the context of the A15 superconductors, which were then the high-temperature superconductors. So I started working on tunneling, microscopic quantum tunneling, in the presence of a bath of fermions, but I found that problem to be much more challenging and subtle than I really wanted to deal with. And Tony was gracious enough to let me work on what I wanted to, which was glasses, so I became sort of an honorary member of Andy Anderson's group here. But eventually, I did manage to get Tony interested in glasses, and we wrote this paper together. So this talk is really the story behind this paper, and I'll end with some more recent experimental results. So let me start by giving you a little bit of background of glasses. Crystal, of course, will give you Debye-specific heat that goes as T cubed. Thermal conductivity also goes as T cubed. If you take those same atoms, jumble them up, form a glass, you find very different thermal properties, in particular linear specific heat. As we've heard about, this is specific heat versus temperature in a log-log plot. And actually, you get something superlinear, T to the 1.22, T to the 1.30. If you look in that region at the thermal conductivity, here's thermal conductivity versus temperature in a log-log plot, you get T squared, and actually it's subquadratic, T to the 1.8. And then between 3 and 10 Kelvin, you get a plateau in the thermal conductivity, and the thermal conductivity rises above that. In that region where there's a plateau, if you look at specific heat divided by T cubed versus T on a log-log plot, you get this bump in C over T cubed, sometimes referred to nowadays as the boson peak. I like to plot C over T versus temperature in a log-log plot, and there you see this rise in C over T between 1 and 10 Kelvin. So these features appear in a wide variety of materials, and the question is, why? The thinking was that, or is that, you have an amorphous material. You've got a energy landscape that's a land of hills and valleys, so each configuration or arrangement of the atoms will give you a different energy. At low temperatures, you might get stuck in some metastable minimum. It's very difficult at low temperatures to move to some other minimum, but you could imagine some local rearrangement of the atoms. And in particular, perhaps an atom or group of atoms could tunnel equally well between two positions, and this could be modeled then as a double well potential, with an atom or group of atoms being able to sit in either one of these wells and tunnel between them. And this was the model of two-level systems or tunneling systems that was proposed by Anderson, Halpern, and Varma and Andy Phillips in 1972. And it's very easy to write down a Hamiltonian for this. It's just a 2-by-2 matrix where the diagonal elements are the energy difference between the minima of the wells, and the off-diagonal elements are the tunneling matrix element, which is the prefactor is basically something on the order of a Debye. You've got an atom tunneling, and the exponent is just given by WKB. And then the assumptions were that the distribution of exponents is flat, and the distribution of these asymmetry energies is flat. And the idea is, of course, it's not flat. It's probably some Gaussian spread over some energy scale, hundreds of degrees Debye or whatever. But you're just looking at 1 degree. And over that small a temperature range, you could probably take a flat distribution. So then the energy eigenvalues would also be constant with this assumption. So then this very easily gives you a linear specific heat. You just write the energy as a constant density of states, occupation factor, that's a Fermi function, the energy, and you take the derivative, you get a linear specific heat. And you can also get then a T-squared thermal conductivity. The thermal conductivity is basically the heat capacity of the phonons. We know phonons are carrying the heat. How fast do the phonons carry that heat? That's the velocity of sound. How far do they get before they hit something? That's the mean free path. And the mean free path, in this case, is going to be limited by resonant scattering of the phonons from the two-level system. So when the phonon energy matches the two-level system energy, it would be absorbed and later re-emitted. And that then gives you quadratic thermal conductivity. OK, so, but what about this plateau in the thermal conductivity that's bumping the specific heat? What do we do about that? Well, if you write the thermal conductivity a little more precisely is an integral over the specific heat, the speed of sound, and the mean free path. The mean free path is a function of temperature and frequency. And you can use that as a fitting parameter to fit the thermal conductivity. And Justin Freeman, Andy Anderson did this. And so if you plot log of the mean free path versus log of the frequency, you get at low frequencies a very long mean free path. Mean free path is about 150 times the thermal wavelength, and that's where you get the t-squared thermal conductivity. Then you see this very rapid fall off. L goes as lambda to the fourth, as Rayleigh-like scattering, and then a very short mean free path, L is of order lambda. One way to describe this phenomenologically would be to say, okay, we have a density of states that are scattering the phonons at low energies, density of states versus energy. Low energies, you have these two-level systems. And then you have a rise in the density of states, some local modes. And this rise would then account for more stuff to scatter off of in a shorter mean free path. And the rise occurs around, say, 10 to 40 Kelvin. So you can use this. So this is consistent with this rise, T over T versus temperature. It's also been seen in Raman scattering, neutron scattering. But you can use that density of states and some scattering to fit the thermal conductivity versus temperature and get these plateaus and also fit the specific heat. Okay, so that's the background. And when I started working on glasses, one of the things caught my eye was some work coming out of Bobby Pohl's group at Cornell, where it's true you don't usually know what the two-level systems are, but sometimes you can deliberately put in something and you say, well, that's my two-level system, and this is the case of KBr-KCN. So potassium bromide has a structure of sodium chloride, and you can take out the bromines and put in these cyanide molecules, which are these big, fat sort of football quadrupoles, strain quadrupoles, and they can reorient in 8 different orientations, and that then is your two-level system. So what Bobby Pohl's group did is they measured the thermal conductivity versus temperature as a function of what happens as you add in these cyanides. And they found that as you add in the cyanides, the thermal conductivity drops initially because you've got more stuff to scatter the phonons, so less thermal conductivity. But at some point, around 1% cyanide, you began to then see the thermal conductivity start to rise again. And I showed this to Phil Anderson. He said, they're talking to each other. And so by that he meant that the cyanides, you have the energy in this one cyanide, it de-excites, emits a phonon that's absorbed by another cyanide. And as they sort of pass energy like a bucket brigade, you've got another channel for conducting heat. So you've basically got this new mechanism for energy diffusion. And I wrote a paper based on that idea of energy diffusion among the cyanide ions. I did ask Phil if he wanted to be a co-author. He declined. But I showed this paper to Tony, and I think it perhaps jogged in his memory some work he had done quite a bit before that on the entropy of systems, in which he pointed out that if you have a diffusion equation describing something in this system, you could have an entropy that went linear in temperature and therefore a linear specific heat. So he said maybe this would apply to glasses, and the idea here is that you have a conserved quantity, locally conserved quantity A, a Bayes diffusion equation. You write the energy in terms of some diffusion kernel, and then that gives you a linear specific heat. If you get greedy and you say, well, you know, there was specific heat was slightly super linear to the 1.3, 1.8. Suppose I want a density of states that you can describe that with a logarithmic correction. If you demand the density of states has that, you can get it if you have an anomalous diffusion. I wouldn't pay attention to this too much because it never really worked. This thing doesn't, anomalous diffusion doesn't even obey dimensional analysis. So, but anyway, it got us thinking. And you know, there was a great deal of discussion, and I was doing a lot of calculations. By this time, I'd moved on to be a postdoc at Los Alamos National Laboratory, so I would come back periodically so we could work on this and discuss it. But the problem was that nothing really panned out, and I didn't actually have anything I could publish. This is a problem because I'm a postdoc. I'm in my sort of last year at Los Alamos, and I'm getting a little nervous. So I gave an invited talk at the March meeting, and John Wilkins was in the audience, and he invited me to write up my talk and put it in his little journal here. So I wrote up the paper. I put Tony's name on it. I showed it to Tony. And he very graciously said, you don't have to put my name on it. It's fine if you want to just be sole author. And I felt, he had contributed to it. And I remember sitting in his office, and I said, look, if I'm the sole author, I'll get all the credit, but no one will read it. If I put you on the paper, you'll get all the credit, but people will read it, and I'd rather have people read it. So Tony agreed to be a co-author. And so I went back to Los Alamos, but once he was a co-author, he jumped in with both feet. He started writing stuff that he wanted in the paper. But the problem is, this is 1988. No internet, no email, there's snail mail. But there is a new invention, a new machine coming on, people are starting to use, called a fax machine. So I suggested to Tony, why don't you fax me what you want to put in the paper? I don't think Tony had ever faxed anything before, but he was aware that there was a fax machine in the high energy group. So he managed to fax me his pages. And it turns out at Los Alamos, there's one fax machine for all of Los Alamos National Laboratory. And so I call up this office that has the fax machine, and I said, I'm expecting a fax from Illinois. Have you received it? And the lady said, well, yes, we received it, but we're going to have to ask them to retransmit because something happened to the transmission, and it got garbled or something. And I thought a minute, and I thought, Tony's handwriting is completely illegible, probably looks much worse after it got faxed. So I said to the lady, that's the way it's supposed to look. I'll be right over to pick it up. And this is the fax that Tony sent me. It actually is missing one page, but you can see I'm trying to decipher what he's written here in the blue ink. So I got this, and I start typing it up, and wrote up the paper and sent it to John Wilkins. You can see he's complaining here. And so let me explain to you what's going on. My style of writing and Tony's style of writing, very different. I was taught that short, simple sentences are good, are clear, that's good writing. Tony likes long sentences, semicolons, and so forth. So I remember typing this thing up. I finally finished the preprint. I put it into the software program that analyzes manuscripts. And it analyzed it, came back, and it said, this paper is written at the level of a senior in high school. But you have a sentence that is 80 words long, and you may want to make a table. So anyway, that was Tony's sentence. And all the semicolons, those are Tony's. So let me tell you a little bit. Whoops. I lost sounds. Okay. You want to just... Okay, this works. All right, so let me tell you a little bit about what's in this paper. Tony has always been someone who always liked the idea, relished the idea of overthrowing cherished beliefs and standard models. So one of the points we make in this paper is that there's no experimental proof of two-level systems. Nobody knows what they are microscopically. There's no proof anything's tunneling, and all the experiments can be explained without two-level systems or tunneling systems. Let me give you a few examples. Phonon Echos, for example, you put in a phonon pulse. This works just like spin echoes and NMR. Put on phonon pulse, wait a little while, put on another pulse, and then you get an echo back. All this implies is that you've got phonons that strongly couple to long-lived states that have time reversal invariance, and they're not harmonic oscillators. You don't need two-level systems to explain that. Another example would be sound attenuation. The idea here is that you're sending in some phonons. They're the ones that match the energy splitting are going to be absorbed. That will attenuate your sound. But if you crank up the intensity and send in more and more phonons, eventually you outnumber the two-level systems at that energy. And these excess phonons get through scot-free. So if you plot the sound attenuation versus log of the intensity, you see this thing, attenuation decreasing. So again, you don't need two-level systems. You just need to say you have a few states that strongly couple to the phonons at a given frequency, and you don't have harmonic oscillators. Another point was that there was no explanation for the universal features seen in glasses. So here's some of the questions that occurred to me. Why is there a 1 Kelvin energy scale? If you look at all the other energy scales in the problem, they're much higher. Phonons have a Debye energy of order 300 Kelvin. Electrons have bond energies that are several thousand degrees. Why do you have all these two-level systems with their splittings of order 1 Kelvin? Another question is, why is the density of states so flat, or roughly pretty close to flat? And why do you have this bump in C over T cubed and this plateau in the thermal conductivity between 3 and 10 Kelvin? What picks out that energy scale? Equivalently, you could say, why do you have this rise in the density of states around 10 to 40 Kelvin? Where does that come from? And another feature was there's no explanation for certain universal values we see. I mentioned to you that the mean free path is of order 150 times the wavelength. Where does this 150 come from? Tony likes to state the problem in terms of the internal friction, or Q inverse, being 3 times 10 to the minus 4. And let me just remind you real quick about what Q inverse is. If you take the glass, you put it on some sort of oscillator, like a double paddle oscillator or something, you wiggle it back and forth, you'll find some resonant frequency, F naught, and some line width. So this is amplitude versus frequency. And you get some line width. That line width is a measure of the dissipation of that oscillator. So Q inverse is the line width divided by the resonant frequency. And if you look at Q inverse on a log scale versus temperature on a log scale, for a variety of glasses, you get things within the range of 10 to the minus 4, 10 to the minus 3. What picks out that value? And finally, the standard model two-level systems did not include interactions unless absolutely necessary. And so there should be interactions. If you think about it, you've got the phonon, which is coupled to the two-level system. So here the E is the strain field, S is the two-level system, gamma is some coupling. And so the phonons, the two-level systems should be able to talk to one another by exchanging virtual phonons, and that would give you a dipolar interaction. If you estimate the size of that interaction, it's much larger than the typical two-level system splitting seen in ultrasound. So you really can't ignore interactions, and I think that's really the contribution of this paper, to say that you really do have to put interactions into the model. And so in fact, this is interactions between two-level systems is now widely accepted. It's certainly consistent with experiment, and there's some experiments you can only explain with interacting defects. Tony went on to, he always had the idea that we could do some sort of block scaling to get these universal values, and the idea would be that you have these little blocks that you could describe by some stress tensors, and then you put in the dipolar coupling between the blocks, you scale to a bigger block, and the hope was that you would scale and flow to these universal values. Unfortunately, and Dervish Viral, who's here, and Tony worked this out, but it never really worked. Didn't really give them these ironclad argument for these universal values. You'd really like something like some topological constant. So it remains a challenge to this day. Let me switch. Does this work now? Okay. Doesn't work. Yes. Okay, it works. Okay, so let me just give a quick experimental update to some things that have happened since then. And the message here is that the defects, I guess we shouldn't call them two-level systems, but Tony likes to call them non-phononic degrees of freedom. These defects are not intrinsic to amorphous materials. And I'm going to show you that their experiment showing thin films, which are amorphous, don't have these low-energy defects. So perhaps this is the exception that proves the rule, which is a saying Tony often likes to say. So one case is indomethacin, which is some organic compound. They make thin films of it, and if they plot the C over T cubed versus temperature, so remember that for a glass, the two-level systems or whatever show up as this tail here, and this indomethacin thin films, they don't see that. And so there's a suppression of the two-level systems. And in fact, they cite Tony's papers in their abstract, And they speculate that maybe the suppression of these low energy defects is due to some reduced isotropic, you've reduced the isotropic interaction between the defects. Other measures of specific heat in amorphous silicon thin films coming out of Francis Hellman's group at Berkeley. Here's C over T cubed versus temperature, and what they've done is change the growth temperature. They changed the temperature of the substrate, and when the substrate's very cold, like 45 Celsius, they see something similar to these low energy defects, but as they increase the growth temperature, then at 400 degrees they get a great reduction. They find that the density of the silicon changes with the growth temperature. So here's the density of the silicon film versus the defect two-level system density of states. And you can see that as you increase the density of the film, you get fewer and fewer of these low energy defects. So they speculate maybe these defects reside in some kind of void, right? You have a lower density, you've got a little bit extra room, you maybe have some little cavity, you maybe have a defect or something, atoms wiggling around on the walls of that void. So there's also evidence from the Q inverse, this internal friction, and the Hellman group with these thin films of silicon. Here's internal friction versus temperature in a log-log plot. This region here is where glasses reside. If you grow it at a higher temperature, you see a reduction in this internal friction. And again, you have the idea that you've made the film denser and less room for these non-phononic degrees of freedom, as Tony likes to call them. There's also some work coming out of Jivac Parpia's group where they took thin films of silicon nitride, again amorphous, and they make a drum head. And so this is a high stress system, and they find that, okay, up here, 10 to the minus 4, 10 to the minus 3, this is where glasses are. 3 orders of magnitude lower, the green points are where you have these high stress internal friction. If you don't stress it, if you make a cantilever like a diving board, then you get, or still the internal friction is less than what you see for glasses. Why does this come about? You know, if you believe in tunneling, maybe there are higher tunneling barriers or weaker coupling of the defects to phonons. Or Peter Salson suggested dissipation dilution. Basically, Q inverse is the ratio of delta F over F naught, the resonant frequency. If you have high stress, maybe you increase the resonant frequency and therefore drop Q inverse. So let me just conclude there. The O model of two-level systems, the way it was stated, is inadequate. There was no experimental proof. We don't know what these things are. We can't explain the universal trends and universal values, and there was no interaction between two-level systems. You've got to really include interactions between these dynamic defects, but we still can't explain these universal values. I think that's still an outstanding problem. And it looks like these dynamic defects are not intrinsic to amorphous materials. So let me just end by wishing Tony a happy birthday, and thank you for your attention. Thank you. Yeah.
Yeah, I think these recent experiments that you're talking about are extremely interesting. But I think that one thing that I'm not quite sure was implicit in what you said was, is there are there cases in which you do get the low temperature thermodynamic properties but don't get the quote universal value of Q to the minus 1? In other words, are the cases where you get a specific heat which looks roughly like T, but Q is way off from 3 times 10 to the minus 4?
I guess if you look at, so this is Francis Hellman's thing. I guess you don't really get, okay, so here is the, you don't have so many, whatever, defects down here, right? But I don't know if that's linear or not. It's kind of a lot of noise, right? If this is C over T cubed, right? So you have linear T gives you a rise that goes up, And so I think I think the answer is, okay, so Tony was asking in these materials if do you have any cases of materials where you get like a linear specific heat, T-squared thermal conductivity, but you don't get the universal value of internal friction, for example. And the only thing I can point to is this, and my guess is no, we don't have such an example, because this doesn't look necessarily like, I don't know, is that linear? Is that going to be linear in temperature? It's too scattered, so it's really hard to tell. If you look at this indomethacin, this does not look like this looks like it's going to be T cubed, right? So it's flat. So I think the answer is no. Peter?
This is more in the way of a comment. I would say, first of all, in my view, and in Vassilchenko's view, the L over lambda equals 150 has been explained by the scenario we present. It's roughly the size of one of these regions, and it does cancel out because of this correlation of TG. This particular experiment of indomethacin is, I hope people do more of it. These are so-called ultra-stable glasses, and they have a larger, they're at a lower effective TG, and their correlation length has been doubled, roughly speaking. And that then means in densities that you're down by a factor of 10. At least in emails, they say that's probably consistent with their data, but they wouldn't say it proves it.
What's down by a factor of 10?
The p-bar.
Oh, okay.
And because C is doubled. So, I think there's quite a few things that glasses made in that particular way are consistent with. Of course, the silicon experiment is odd. Silicon is also very strange because it's supposed to be amorphous, but it's anisotropic. So it's not exactly a poster boy for just a simple amorphous substance, actually.
Right. So no, I'm aware that your theory did give a way to get the 150. I think the thing that left me uncomfortable was or not absolutely sure, was that there was the estimate is a quantity A over your correlation length cubed, and if I just change some of those estimates by a factor of 2, suddenly I'm off by a factor of 8 because it's 2 cubed. So, but I am aware that you're getting things in that ballpark. Kristen.
Just a small comment. When you plot the specific heat, you were pointing out that there's a small deviation from the linear dependence. That has always been a debate, because when you measure specific heat, it changes with temperature, which it shouldn't, of course, as a state property. But in glasses it does, because there are some very slow relaxating systems. And therefore, this was a measurement you showed where I think they took 1,000 seconds per point. So if you wait longer, it gets closer to linear dependence. And if you analyze it in a different way, not just taking the data at this time, so you extrapolate the distribution of times, then you end up with a linear dependence. So I showed the same data, but they were linear dependence. They were analyzed in a different way.
Okay. All right. Interesting. Thank you. So are the phonon echoes, the time scale similar for phonon echoes and for microwave echoes? Christian, you answer that. You do echoes.
Well, experimentally, the accessible time range, you mean? Or you mean the
The
decay
tau,
times?
the T1,
yeah.
the
They're
T1,
very similar.
I think they're similar.
People have also done cross experiments where they excited phonon echoes and looked in electric fields and such, and they're very similar.